So please come in and take a seat. Let's give them a few seconds to sit down.
So can I move this?
I'm just going to introduce you.
Okay.
All right, welcome to Reinforcement Learning 8, the 8th Reinforcement Learning session out of, approximately several thousand. Our first presentation in today's session will be Convergent Tree Backup and Retrace with Function Approximation, and Ahmed Touadi will be presenting.
Thank you. Yeah, so my name is Ahmed Touati. I'm a PhD student at Mila University of Montreal. And I'm happy to talk about convergence tree backup and trace with function approximation. It's a joint work with Pierre-Luc Bacon and Doina Precap at McGill University, and my supervisor, Pascal Vincent, at University of Montreal and Facebook AI Research. So in this paper, we are interested in off-policy evaluation, which aim at estimating the performance of target policy using different stream of experiences generated by behavior policy. And this provides many benefits, such as reuse of past experience via experience replay and efficient parallel exploration. We are also interested in multi-step learning, as it enables rapid propagation of rewards, and it can produce much superior solution than one-step learning when combined with function approximation. So in this work, we are interested in two online multi-step of policy algorithms, which are tree backup and the trace. So firstly, we show instability of both algorithms with function approximation. Then we derive convergent gradient-based of policy algorithm, and we provide their finite sample analysis. And finally, we show that our finite sample analysis improve the conversion rate of existing gradient temporal difference algorithms such as GTD and GTD2. So let's start by some background. So in off-policy learning, we distinguish two policies. So we have behavior policy mu and target policy pi. We execute the behavior policy to generate trajectory, and our goal is to estimate the action value function for the target policy pi, which is defined by the expected cumulative discounted reward. So one way to do this is to use importance sampling. So importance sampling method correct off-policy return in terms of transition probabilities by scaling the returns by the product of importance sampling ratios. And this has an issue of introducing large amount of variance, and that makes hard to learn with multi-step. So instead of correction in terms of transition probabilities, there is another family of methods that directly correct immediate reward based on the current approximation of Q function. So we introduce here the expected temporal difference error, which is similar to the classical temporal TD error, but here we have expectation over action according to the target policy. And the whole family of this method can be seen in unified view via this lambda return. And each algorithm differs according to the value taken by kappa. For instance, for Q pi lambda, kappa is always equal to 1. For tree backup is equal to the target probabilities, and for trace is equal to the truncated importance sampling. And in terms of convergence, it has been already shown that Q pi lambda converge when mu and pi are close, while tree backup and trace converge for any mu and pi. But this convergence result results are restricted to tabular case, and so natural question we answered in this paper: what's the behavior of those algorithms with function approximation? So let me introduce some setup. So we focus on linear function approximation. So we approximate our Q value by inner product of between a weight vector and the feature vector. And the turbulent difference updates is as the following. So we incorporate the lambda return of retrace and tree backup in semi-gradient fashion. So it's not actually true stochastic gradient descent. And so one way to analyze the dynamic of this update is to establish its expected behavior. So in particular, we can express the expectation of the next iterate condition of the current iterate as a fine transformation of the current iterate, and involving a matrix A and the vector B, which we can compute in closed form. And let me explain what are the quantities involved in those two quantities. So we have Xi, which is the diagonal matrix of stationary distribution induced by behavior policy mu. Phi is the feature matrix. P pi is the probability transition matrix. and P kappa mu is the sub-probability transition matrix. And we can consider this expected recurrence as discretization of differential equation, and we know as a classical result from stochastic approximation literature that if A is a negative definite matrix, so the iterates converge to the unique asymptotically stable equilibrium of this differential equation. So in the on policy case, when mu is equal to pi, so we can prove that A is negative definite, and we rely on the fact that the stationary distribution is invariant with respect to transition probabilities. But in the case of policy, this is not true, and we will investigate what happened to the matrix A in a simple environment. So we consider this environment consisting in two states. And we have the possible action is going left and going right. The target policy is given by is always going right, and the behavior policy is uniform over possible actions. And in this very simple setting, we can compute exactly the matrix A, and we can show that the matrix A would have positive eigenvalue, and hence the iterates diverge in expectation. As experimental evidence, so we implement tree backup and tree trace, and we see, for example, in the right figure, they clearly diverge, and the other figure, it's actually our new algorithms that converge, and I will explain later. So now we know that tree backup and tree trace diverge, might diverge. So how to fix that? So a starting point is the observation that if theta star is the optimal solution, then phi theta star actually is the fixed point of the projected Bellman operator. So this projected operator formed by two parts. So we have the operator R that correspond to tree backup and retrace or tree trace return, and then we have pi mu, which is the orthogonal projection onto the space spanned by the features with respect to the Euclidean norm weighted by the stationary distribution. So one way to reach this optimal solution is to minimize directly the mean squared projected Bellman error, which is the squared distance between phi theta and its image by the projected operator. And we show that that this also is equal to the square distance of A theta plus B weighted by the inverse of the feature covariance matrix. So to optimize this, to minimize this objective, so one way we could compute gradient with respect to theta, but then we will obtain the gradient as product of expectation. So it's not straightforward to obtain an estimate, an unbiased estimate of this gradient, which is known as double sampling. And one way to fix this is to do ad hoc to time scale stochastic approximation, but then the obtained algorithm will not be a true stochastic gradient descent. So a principled way to minimize this objective is to cast our minimization problem into saddle point using differential duality. So here, just remind what is the convex conjugate of function f. And in particular, we will use the fact that the convex conjugate of the square norm weighted by matrix M is equal to the square norm weighted by the inverse of this matrix M. And then we are able to cast our minimization problem to a saddle point problem where we introduce a dual second parameter, omega, which is the dual variable. So now to optimize this saddle point, so we just apply gradient update. So we have gradient ascent for the dual parameter and the gradient descent for the first one. So till now we have only this is deterministic update. So the next step is how to derive a stochastic update, because we are interested in the online setting. So to do this, actually we will introduce this eligibility traces vector, and this is derived by exploiting the equivalence in expectation between forward view and backward view. And then if we consider this quantity a hat, which is equal to outer product between the eligibility traces vector and the difference between the expected future features and the observed features, B as a product between between the reward, immediate reward, and the eligibility traces vector, and M as the empirical covariance matrix. So we can prove that those quantities are actually unbiased estimate of A, B, and M. So now we can use those quantities to have a stochastic update for our algorithms. So now that's leads me to the third main result of our paper. So we have propositioned that state if the step size decay in 1/k, so there exists a coefficient beta such as the second step size. If the second step size is proportional to the first step size by this coefficient, then the square distance between our iterates and the optimal solution is bounded in an expectation by two terms. So the first term is a bias term, which tells that the initial error is forgotten at rate 1/k⁴, and the constant depends on the condition number of the covariance feature matrix. And the second term is the variance term, and tells us that the noise is rejected at rate 1/k, and the constant depends on the variance of the gradient estimates and the condition number of M. And the overall convergence is in 1/k, of course. Actually, our finite sample analysis is not restricted to our new algorithm, but also can be applied to existing gradient-based TD algorithm, such as GTD and GTD2. So let's do a closer look at the convergence result in the literature. So those this algorithm were introduced by Sutton and al. In 2009, and they established the asymptotic convergence. Then later in 2015, Liu and al. Established for the first time the finite sample analysis of this algorithm. But actually, he studies an altered version of the algorithm by introducing a projection step into a bounded convex set to avoid the divergence of iterate and the Poiliac averaging. And he established 1/square root of k as conversion rate. And later, NIPS last year is the paper that studied the same version with projection and Poiliac convergence, but with general schedule of learning rate. But the optimal rate is still 1/square root of k. And this year at ASTAT, so there is this paper that improved the conversion rate to 1/k, but still using Poiliac averaging and constant step size. And our work is the first time that we studied the original version of GTD and GTD2 algorithms, without projection step, without Poiliac averaging, and with diminishing step size. And we have 1/k. As a conversion rate. So we also, in the paper, we have also some comparison with other state-of-the-art convergent of policy algorithm, such as GQ and Abitrace. And for more details, you can go to the paper. But our experiments suggest that our algorithm has less variance. So that leads me to the end of the talk. So as summarize, so we highlight the difficulty of combining tree backup and trace with function approximation. Then we derive an online gradient-based algorithm version using saddle point formulation. And at the end, we also provide a finite sample analysis of our algorithm, and we show that this analysis improved existing conversion rate of existing gradient TD algorithms. And thank you.
plenty of time for questions. So if you have a question, there are microphones on the sides. So yes, please go ahead.
Hi, I'm Gal. I have two annoying comments. First, that's not a 2-time scale algorithm, right? Because the step size ratio doesn't decay. And the second annoying comment is that it's actually not the first work. We presented some work recently, and it was in court this week, on 2-time scale stochastic approximation with, without projections. And can you go back to the table?
Of course.
And with no Pollyak averaging as well. So.
Okay, so
But I guess if you want, we can talk about it in the poster.
okay, so it's work that is presented at this year.
Yeah.
Okay.
I mean, it's been on archive for a few, from 2017. But I would say that the convergence rate that we get is not optimal. So we get a k to the minus 2/3 at best.
Okay.
So 1/3, I'm sorry. But yeah, it's worth discussing.
Okay, but for the first comment, you said that our algorithm is not 2-time scale stochastic approximation, right?
Yes.
Yeah, which is true. We didn't claim this.
Oh, okay.
No,
I thought at the
actually,
beginning you said it is a
No. Actually, we are discussing two ways to minimize this objective. So we can use 2-time scale stochastic approximation, and other way to do this is to cast our problem in saddle point. So we use the second alternative. So yeah, I agree with you. It's not a 2-time scale stochastic approximation, and maybe actually the analysis you provide maybe doesn't work for ours, because it's a different setting.
Yeah, okay.
But you can.
It'd be interesting to discuss it actually, because
of course.
you know, when Chaba is here and the first folks, sorry, but they kind of argue that you need to do 2-time scale stochastic approximation to decouple the expectation and the gradient estimation, and that kind of disappeared from 2009, and then so it's worth discussing, I guess. Maybe we should discuss it. Yeah.
Okay. But in our case, we don't need 2-time scale stochastic approximation.
Yeah, nice work, thanks.
Okay. Thanks.
Could the next speaker start coming up? And in the meantime, we do have time for another question if anybody would like to ask one. Back there.
Thanks for your talk. Did I miss it? Did you actually show the algorithm in the slides?
No, I didn't show the entire algorithm in the slide. I just have. Actually, I have this as deterministic, but then we have to replace the quantity A, B, M by their unbiased estimate, which is defined using the eligibility traces vector.
So it's a.
But I have in the paper the entire algorithm, but not in the slides.
So the algorithm is it order D or is it order D squared?
No, it's order D, because actually all the unbiased estimates are one rank estimation of the matrix. So we don't do a multiplication matrix vector, but actually it will be we have scalar product times a vector. When you take this matrix A and we, for example, this matrix A hat, and we multiply it by theta, so this will be a scalar product times the eligibility traces. So there is no, it's not product matrix vector. So it's linear.
I'm worried about M. You had an MK. Do
Yeah,
you maintain an estimate of M?
Yeah, M is the same also, because M, we have to multiply it by omega. So it will be it will be the inner scalar product between omega and the feature times the feature, observed feature. So there is no matrix vector multiplication, and all the algorithm is in linear time.
You don't have to maintain any matrices.
No matrices. I can show you later if you want the.
Okay.
The,
cool, thanks.
the entire algorithm. There is no there is no matrix vector multiplication.
So unfortunately, we do need to move on to the next speaker, but of course, the presenter will be at the poster session later, and you're welcome to ask your questions then. Our next presentation will be entitled Speed, Convergent Reinforcement Learning with Nonlinear Function Approximation, and Li-Hong Li will be presenting.
Good morning. My name is Li-Hong from Google. Today I'm presenting joint work with my colleagues and Bodai, Albert Shore, Lin Xiao, Niao He, Zhen Liu, Jianshu Chen, and Le Song from multiple places. And the title is, the more technical title is Convergent Reinforcement Learning with Nonlinear Function Approximation, and I changed the title a little bit as first part, Speed out of the deadly triad, and explain why shortly. So let me start with a slide that summarizes the main results of this talk. So as a background, for the purpose of this talk, and the majority of, well, a large fraction of RL papers in the literature, the essential key of solving RL is essentially using data to solve the Bellman equation for optimal policies or value functions. And the majority, well, and the powerful class of algorithms, and a very popular one, is based on the idea of approximate dynamic programming that includes algorithms like DQN and others that people find very useful. But these algorithms, unfortunately, are inherently unstable. And this problem of finding an alternative or fixing this convergent problem has been an open problem for decades, and recently it even got its famous name, deadly triad. In this work, we approached the problem of solving the Bellman equation from a different perspective. We reformulate the problem into a primal dual optimization problem. That's the first contribution. And the second one is to provide the first convergent ADP, approximate dynamic programming algorithm called SPEED, that works with general function approximation and is guaranteed to converge under certain assumptions, pretty standard assumptions. And the last one is an empirical validation of the algorithm on standard benchmark, and it outperforms a number of state-of-art baselines. Okay? So let me give you some background of the problem, more details of why the convergence is a problem. This is the standard slide of all the RL talks maybe, and the notations of state of action is S. A is a set of actions, and the transition probabilities, reward, and discount factor gamma. Okay, this is all standard. And then, so here's the Bellman equation for, and we all know that the optimal value function V star solves the Bellman equation, which says that the optimal value of a state, long-term value, equals the one-step reward plus future optimal value if you choose the optimal action. And for convenience, let me write the right-hand side as a T of V. T is a Bellman operator. Essentially what it does is to take a value function, V star in this case, as an input, and outputs another value function. So TV star is another value function. And it's well known that this operator, T, is gamma contraction, meaning that you start with two value functions, you apply the operator, you're guaranteed to move this function closer to each other. And as a consequence, you can show that if you apply the operator many times, it converges to V star, which is the fixed point of the operator. And this is the mathematical foundation for a wide class of algorithms such as Q-learning, TD learning, valuation, etc. In the exact case where you can represent the value function exactly. But in reality, when the problem becomes very large, it's impossible to represent the value function or policy as a table lookup. So essentially, all you need is use function approximation. For example, use least squares regression approaches pioneered by Gauss hundreds of years ago, or on linear models or neural networks. Unfortunately, when you combine this operator and the function approximation, you lose the contraction property. Therefore, it's possible to construct very simple and well-known divergence examples where dynamic programming with approximation may diverge. And there's limited theorem for special cases, essentially mostly for value iteration or, for policy evaluation or for linear cases, or when you have a special kind of function approximation classes. And this has been an open problem for decades. This is perhaps the oldest paper I can find for using the function approximation in dynamic programming in almost 60 years ago. In practice, this sort of instability things can happen. So you can, people may realize that when you train DQN or other popular algorithms, the learning curve jumps up and down, and sometimes the Q function on the bottom left goes up and then go down. Sometimes the bottom of the top right, the Q function chatters between several regions. And my favorite example is the divergence, where you simply have a wave that goes to infinity no matter how you tune the step size. And this can happen in practice. I have seen it myself. And 3 years ago, there's the deadly triad starts to be famous, which essentially says that it's very difficult to find an algorithm that is not divergent when you have a function approximation and when you use bootstrapping for more efficient reinforcement learning and policy data, where your data does not necessarily come from the policy that you choose. So given this difficulties, how can we avoid this, address the problem? So a very natural idea is is the follows. I want to solve a fixed point. So a natural idea is to minimize the Bellman error, which measures the discrepancy between the left-hand side and the right-hand side of the Bellman equation. But if you write down the closed form, it's not a nice objective function to optimize. First of all, there's a max operator that breaks the continuity and smoothness. So it's hard to optimize. That's the first one. The second one is related to the conditional expectation inside the square. Essentially what it says is that it leads to the double sample problem. So what it says is that if you have a single sample S prime given S and do gradient descent, you're essentially approximating the right-hand side of the bottom equation using one single sample. But then this is not exactly the same as the left-hand side that we actually want. So let's address these two difficulties one by one. For the first one, we can use the Nesterov smoothing technique. So remember in the Bellman equation, there's a max over A step there. Now we introduce a regularization, entropy regularization of the policy. And then instead of maximizing over A, I maximize over a set of stochastic policies. And when lambda is not 0, then obviously usually the optimal policy will be, after smoothing, will be stochastic. And this operator has been derived from different principles for different purposes. Here we use it to get rid of the max. And the second, so now without this max, let's call this new operator smooth Bellman operator. It has a few nice properties. For example, it's still a contraction. You can control the bias from the original problem by making lambda small. And finally, and most important for our purpose, is the temporal consistency condition, as in previous work, path consistency learning of Natrum and colleagues. What it says is that if you try to solve this fixed, smooth Bellman equation, the solution satisfies this equation. For any state action pairs, even if the action is suboptimal, it has to satisfy this equation. The intuition is that if the action is not optimal, the first term and second term, the sum of the first two terms on the right-hand side is small, but then it's compensated by the last term, the regularization term. And pi will push that suboptimal action to a small value. And overall, the right-hand side is the same for all actions, and this equals the value of the state. So this temporal consistency equation leads to this very natural objective function on the top. I can just sample states in any distribution I like, and then minimize the second one. After smoothing, I can minimize the objective function on the second line. So now I can get rid of the max. The second thing is the conditional expectation, and I'm going to use the same trick that the previous talk also used, which is the Lagrange differential transformation. Essentially, the difficulty of having the double sample problem is that there's a random variable inside of the square. So I want to move the random variable outside of the square. And one way to do it is to use this transform using the dual of the square function. By introducing a dual variable, now it becomes linear. So x sub SA, for any SA, is a random variable. By introducing a dual variable y, I can move it outside of the square. And then there's one subtle issue called that we need to use, the interchangeability principle, to change the y, which is a real value, to the nu, which is a real value function on state action pair. So there's some mathematical subtlety, but at the end of the day, what we have here is that we can get rid of the double sample problem by introducing a dual function, and then we end up with this final form of modified framework. So instead of finding a fixed point for the original Bellman equation, now we're trying to solve a primal dual or saddle point problem. And this has many benefits, but let me briefly describe the idea of the algorithm. Oh, by the way, I should have mentioned that in the last line, when you do the max, internal max, the internal max is achieved when nu equals the lambda smooth Bellman error. It's easy to verify that. And because of that property, we gave the algorithm the name of SPEED, smooth Bellman error embedding. So the idea is quite straightforward. Once you have the saddle point formulation, you have a well-defined objective function inside the minimax, and then all you can do is to use first-order information to do gradient descent or ascent or things like that, where you parameterize these variables, primal variables v and pi using neural networks, for example, and then the dual variable nu by another neural network. And then there are many advantages of this algorithm. I'd like to just highlight one or two. The first one is that the algorithm is agnostic to the distribution of data. It can be collected either on policy or off policy. The algorithm does not care. The algorithm may be used in a batch mode, for example, in experience replay or in online mode where you have more and more data as the agent acts online to collect more sample. And it can be extended to eligibility traces and efficiently implemented. So here's a little bit of theory. It's a little bit, there are many more details to describe the complete picture properly, but essentially what we have for the theory is that this is a stable and convergent algorithm. More specifically, if you define the inner optimization problem, well, you get rid of the max, inner max, and define L bar to be the function where the inner max is solved. So this is just a conceptual definition. If that function, L bar, is Lipschitz continuous, and its stochastic gradient has finite variance, and you set a step size properly, then this speed algorithm will output a solution as you keep the iteration going on. It will eventually output a solution whose first order diminishes, well, its gradient diminishes. And the proof essentially builds on the results of Gadimi and Lan in 2013. And this is just one version of the convergence guarantees. And there's different variants that you can play with the conditions and end up with slightly different convergence guarantees. And we also have statistical and generalization analysis in the paper. So very briefly, let me show you results on the Majuko. So we compare to three algorithms. Dual actor critique is another algorithm Bodai and I and other colleagues published at iClear, and TRPO and then DDPG, both state-of-the-art algorithms. First of all, this plot shows you the role of the smoothing parameter lambda. The x-axis is the time steps, number of iterations used to optimize the objective function. The y-axis is the reward, and higher the better. So, and then different curves correspond to different values of lambda. When lambda is smooth, essentially you don't do much smoothing, and it's harder to optimize, but you have a higher bias compared to the original Bellman error solution. But if you increase lambda, then the opposite things can happen. So hopefully, intermediate values of lambda is the best, as confirmed in this plot. And then the second set of experiments is are the comparison on 5 problems in Majorco. The x-axis is still the number of iterations, and the y is the reward of the resulting policy, higher the better. The blue line is this curve for our algorithm speed, and the others are dual actor critique and TRPO and DDPG. As you can see, on these problems, speed actually learns very fast and reliably, except for the half cheetah that it takes a little bit longer to catch up. But still, pretty soon, it beats the baselines. And one thing I should highlight is that speed can be used in policy manner, meaning that you collect all the data, you can use the same set of data or to do optimization, or if you do it online, you can keep all the previous data to do the optimization. Compared to the vanilla version of TRPO or on policy version, you have to collect more samples. In this sense, speed can be much more sample efficient, and that's one reason why you see this big gap of performance. So to conclude, just a recap, in this work, there are several contributions. One is to primordial reformulation of the Bellman equation for reinforcement learning. And the second is the new algorithm speed that are guaranteed to converge under certain assumptions. And it works for general function approximation as long as you can compute a gradient. And the last one is empirical validation on the standard benchmark. Here, further remarks. First of all, I think there's a lot of interesting future directions to explore. I think the primordial gives a different view of how to approach the reinforcement learning problem, and I think in the future, there are different ways to extend this work to a rich set of problems in reinforcement learning. As an appetizer for future thoughts, I would like to mention that you can specialize speed by removing fixing the policy, by using linear function approximation, etc. And speed will give you the TD solution, the fixed point solution. So there is a lot of connection between this new algorithm and previous ones. Just they're not different, and they do overlap in special cases. And then finally, this is an example of a sequence of work that tries to derive gradient-based reinforcement learning methods starting about decades ago by researchers in Alberta and other people, Sutton, Chaba, Marie, etc. from GTT2. And it turns out that there's a deep connection between these algorithms to optimization. And more recently, this connection has resulted in many stronger and better algorithms. For example, a whole bunch of these, and even the previous work also used some of the optimization techniques as a key step. And finally, the last one, Chen, happens to be the next talk, and is also an example of how optimization can be useful for reinforcement learning. Okay, so I think I'll stop here, and thanks.
All right, we have time for a few questions, and maybe the next speaker could start setting up while we ask the questions. So there's a question in the back there.
Hello, Li Hong.
Hi, Rich.
So I have to ask the obvious question. The special thing about your work is you're looking at the Bellman error rather than the projected Bellman error. And the other methods have all worked with the projected Bellman error. And as you know, I've also presented what I consider a counterexample to proving that there's no way you can learn the Bellman error. And and I know you've looked at that, so what's the resolution? Are you actually learning and minimizing the Bellman error, or are you minimizing the projected Bellman error like the other methods?
Good question. So in this work, I haven't specifically distinguished Bellman error versus projected Bellman error. So we start with the goal of solving the fixed point of Bellman equation, minimizing the left-hand side and right-hand side discrepancy. And through the derivation of the algorithm and formulation, we introduced a dual. And it seems that because of the introduction of a dual variable, you end up with something that has the flavor of a projected Bellman error as an objective function. As I mentioned at the end of the talk, When you specialize the algorithm for linear functions and policy evaluation, it does give you TD learning solution. So in that sense, it's still optimizing projected bound error. Yeah. I can change the name of the algorithm to projected speed.
Okay, let's go with a question over there.
Thank you very much for the talk.
Thanks.
I'm curious what exactly the convergence point is. Do I understand correctly that lambda basically controls how much bias that convergence point has?
Good question. In general, I think it's pretty hard to specify the convergence solution. But I suspect that for simpler classes like linear, it's possible to actually have a deeper understanding of what's going on. But essentially, this is popular techniques in optimization. Yeah.
Thank you.
Thanks.
All right, last question over there.
Hello, thank you for the talk. I want to ask about the lambda parameter. As far as I understood, if this parameter is not 0, then we are not converging to the optimal policy. Mm-hmm. So how can we see it? Meaning, if I take the limit, I would expect that I would not converge to the optimal policy, and in fact, that I won't have any convergence.
Also, good question. There seems to be a phase transition when you move lambda towards 0, or sometimes when it becomes 0. I think it is a point that deserves more thoughts and research. But this is a great question.
All right, so now we'll move on to the third talk of the session. This is Scalable Bilinear Pi Learning using State and Action Features, and Yichen Chen will be presenting.
It's my pleasure to introduce our work, Scalable Bilinear Pi Learning. It is a joint work with Li Hong, who has just gave his nice talk, and my advisor, Mandy, from Princeton University. Reinforcement learning has seen a huge success in recent years in controls and games. So usually, reinforcement learning is modeled by Markov decision process with a finite set of states S, action space A, transition probabilities PA, and rewards R. So in reinforcement learning, we want to find an optimal policy that can maximize the long-term average reward. So in our case, we are focusing on the long-term average reward compared to discounted reward. And besides, we do not know the reward and the transition probabilities. So instead, we have a generative model that can generate the samples according to our controls. And also, we are interested in sample complexity, which is the total number of samples queries to the model in order to find epsilon optimal policy. So the sample complexity has been studied in the literature for many years. So here I list a few results. So in all these results, the sample complexity has a linear dependence on the state number, action number, 1 over epsilon square, and also factors like 1 minus gamma. And also in our primal dual pi learning algorithm, the dependency is on the mixing time. Actually, the existing sample complexity results matches the best information theoretical lower bounds. But the issue here is that the sample number S could be very large. Even you could have like 1 billion samples which make these bounds vacuous. And our question is, can we actually do better that even break the lower bounds? Can we actually have linear dependence or better dependence on state and action number? And our answer is yes, when we have the state and action features. So let me explain the intuition. Okay, let's say we are playing the game of Dota. It's well known that if we are facing a similar situations, usually the optimal actions are similar. So how do you actually measure the similarity between states? This is where we have features. So let's say we have a feature phi that can map a state S to feature vectors. What makes a feature a good feature? Suppose that the transition, the probability transition P, actually only depends on the feature of a state instead of the state itself. Okay, if we suppose that, and now if we have two states S and S1, they share the similar features, then the value of S1 and S2 will be the same. And besides, the long-term probability of the visiting probability of S1 and S2 should also be similar. And more importantly, if the reward is the same under S1 and S2, the optimal action at S1 and S2 should be similar. So next, we show how to use these given features to actually make reinforcement learning more efficient. So recall the Bellman equation for average MDP is as follows. I won't go into the detail of Bellman equation. What I want to mention is that actually the Bellman equations can be rewritten as a saddle point problem. So in this saddle point problem, the primal variable is the value function. And the dual variable corresponds to the long-run state action distribution. And the dimension of the saddle point problem is very large with dimension SA times S. But rewriting this Bellman equation, this saddle point problem itself does not help us to reduce the complexity. So how to reduce the complexity? And this is where the features come into play. So in our work, we assume a bilinear model of model reduction. So we are saying that the value vector actually is a linear combination of its features. So using the language of linear regression, V here is the outcome, phi is the regressor, and the VI tilde is the parameters to be learned. And besides, we have a similar decomposition of the stationary probability mu A. And given this stationary probability, we can parameterize the policy where we are taking the policy is proportional to this stationary probability. So given our model, our bilinear model, we would have a reduced order saddle point problem. So here, we don't need to actually search over decision variable with dimension S. Instead, we have low dimensional primal and dual variables. And actually, a side question is how to actually obtain these state and action features to preserve the dynamics. I want to advertise another work by our group called the state compression of Markov process, which is on Friday. Okay. So after we have our reduced Markov Bellman equation, we can design, we designed a model-free, sample-efficient, and space-efficient algorithm for solving the reduced order saddle point problem. So our algorithm is as follows. In each iteration, our first thing to do is we sample a state and action according to our controls. And then we alternatively do a value update and a policy update. So our algorithm is sample efficient because in each iteration, it only needs one sample. And it is also space efficient because it does not need to store the state. So instead, it only requires and it only needs the state features. And after that, we will project the iterates back to its constraint and project the dual variables to its space. So we have following convergence analysis of our results. So our bilinear pi learning method finds a near optimal policy using time steps in the following way. So the first term is actually the convergence arrow of our results, and the next two terms are actually the approximation arrow. So here, the tau is, depends on the stationary probability, T mix depends on the mixing time, and the C phi is parameter depends on the features. So here, the approximation arrow depends on how well the state and the action preserve the dynamics of the underlying Markov decision process. So assume that the optimal value distribution is realizable by our features, which means that actually the approximation error is 0, and then the sample complexity will have taken the following terms. So what's important about this sample complexity is that it only depends on the number of features, action features and the state features. It doesn't depend on the state number and the action number. To summarize, in our work, we propose a bilinear model for reducing the dimensionality of the reinforcement learning. And the second, we provide a primordial algorithm that is sample efficient, space efficient, model free for learning the near optimal policy. And the last, we showed approximation guarantee of our algorithm and the sharp sample complexity analysis of our results. Okay, thank you very much.
All right, could the next speaker come up and start setting up? And in the meantime, we have time for maybe one short question.
So thanks for the very good talk. So how do you comment or compare with your set point formulation with the previous talk?
Actually, it is, how to say, so because our work is about the optimization problem, so in the previous set point, it's kind of different. So because in the because our, how to say that? Yeah, because I haven't been to the previous talk, so I'm not sure about that set point. Maybe we can discuss about that offline.
All right, let's thank the speaker one more time.
Sorry.
The last talk of today's session will be Stochastic Variance Reduced Policy Gradient, and Matteo Papini will be presenting.
Hello, everyone. I am Matteo from Politecnico di Milano, and this work is joint between Politecnico and INRIA. It's called Stochastic Variance Reduced Policy Gradient, SVRG for short. But let me start from that policy gradient part. So policy gradient is a very effective reinforcement learning technique where you learn a parametric policy to solve continuous or high-dimensional control problems. Here we have just two examples of applications from robotics and video games, but there are many others. These are impressive achievements, but they're mostly based on a rather old and simple optimization technique that is stochastic gradient ascent. So you have a parametric objective. You want to maximize, in this case, the performance of your agent. And you do that by iteratively updating the parameter by following a gradient that is estimated from data. So stochastic gradient ascent was first proposed as a more efficient alternative to traditional gradient ascent, where you can update your parameter with just one data sample. And this is fast, of course, but in time, the data sampling introduces variance, and this slows down the convergence. On the other hand, if you use all the data you have to compute your gradient, a full gradient, the convergence asymptotically is better, but if you have an unlimited amount of time, this is inefficient because to compute each update, you need to process a lot of data. So it seems we can do something better optimization-wise. And there are already many solutions to this. A popular one is stochastic variance reduced gradient, SVRG for short, by Johnson and Zhang. And this comes from finite sum optimization, where your objective can be decomposed into the sum of elementary functions. The idea is that you combine the stochastic gradient and the full gradient into a new gradient estimator. And the trick, is that, yes, you compute your stochastic gradient frequently, but this is inaccurate. And you combine it with a full gradient that is more accurate but expensive, but is just computed once per epoch, that is every m iterations, so that you reuse these gradient computations. And you just have to add a correction term to make this unbiased. This can be proved to have linear convergence, just like the full gradient, and is clearly more efficient. It is quite straightforward to apply this to supervised learning, but this is not the optimization session, so what about reinforcement learning? Well, here your objective is actually an expectation over all possible trajectories of experience, and this makes it more difficult to apply SVRG. So far in the reinforcement learning literature, we have seen applications of SVRG to policy evaluation and offline control, but it's only in on-policy control that you have all the complexity of the RL problem. There are three main challenges. First, your objective is almost always non-concave. Second, you would need infinite data to compute just one full gradient, so you have to use an approximation. And finally, and this is very specific of on-policy learning, each time you update your parameter, you are updating your policy, and so your data sampling distribution. And this is a source of non-stationarity that typically you don't have in supervised learning. So we have to face all these challenges at the same time, and to do so we propose a stochastic variance-reduced policy gradient, SVRPG, where the full gradient is estimated with a large batch of n trajectories, and your stochastic gradient is estimated with a much smaller batch of b trajectories. Of course, these are fresh data from your current policy, while the full gradient, or its approximation, is computed in this snapshot policy, and then it is reused many times. Another aspect is that your correction term in this case has to include an importance weight, and this is to account for the non-stationarity I discussed before. And of course, this correction is not for free. It makes the SVRPG estimator unbiased, but it is a novel source of variance. So this is clearly more data efficient than just using full gradient. And please note that it is on policy because the importance weighting is just applied to the correction. So what about the convergence? Well, we are able to show that it has linear convergence plus some error terms. Of course, the convergence is to a local optimum because the objective is non-concave. Then what about these error terms? Well, one comes from your full gradient approximation, while the other one comes from the non-stationarity that I've been talking about. You can make these terms negligible by taking sufficiently large batch and mini-batch sizes. But there is another way. So these constants here depend on interesting metaparameters, namely the step size of the gradient update, of course, and the epoch size, so how often you take the snapshot. Of course, this guarantee holds for very conservative choices of these metaparameters, as is often the case in optimization. But in practice, we can use heuristics to select these hyperparameters as to maximize efficiency. Our solution is based on ADAM. For the step size, we keep two separate annealing schedules because the full gradient and the stochastic gradient have variances of very different magnitudes. And for the epoch size, we simply take a snapshot as soon as the effective step becomes too small. That means we need more fresh data. So we compare these to plain stochastic gradient, in this case the GPOM-DP algorithm, on benchmark control tasks, including a couple of MuJoCo tasks. And we see an advantage over plain stochastic gradient. Here the average return is plotted against the number of trajectories, so that you can appreciate the data efficiency of our algorithm. The advantage is less clear in this more challenging task that is Alf-Cheetah, but please note also how the variance of the return is visibly reduced. Here, our algorithm is in blue and GPOM-DP is in orange. to conclude, there is still a lot to be done. We have seen why using SVRG in reinforcement learning may be a good idea and what are the challenges. And now we should combine these with other reinforcement learning techniques. I think the main take-home message here is try to use SVRG in your policy gradients. If you want to know more, we are at poster 65, and thank you for your attention.
All right, we have time for a few questions. If anyone has any questions, please step up to the microphones. So I have a quick question I wanted to ask. So in practice, oftentimes for these kinds of policy gradient methods, we would use something like a natural gradient or a variant thereof. Do you have any comments about how your method relates to natural gradient? Is it something that you think can be combined directly, or?
Yeah, this is a good question. Actually, we left this for future work, but it would be very interesting to try to combine this with natural gradient, because with natural gradient, you have more control on how the distribution of the trajectories change, and so they could, combining them could be very useful.
There's a question over there.
Thank you for your talk. It's very interesting. It sounds like your algorithm is not online. It rather takes a bunch of trajectories and so have you thought, is it possible, is that correct? And have you thought about a possibility of a truly step-by-step online algorithm?
Oh, I see. Yes, this is still trajectory-based, so you collect, as you have said, the whole trajectory. I guess it would be very interesting, but yeah, it's for future work. Thank you.
Okay, let's thank the speaker one more time. And this concludes Reinforcement Learning 8. All the speakers will be at the poster presentation in the evening, and thank you very much for your attention.